All right. Yeah, one of the things that I have in sort of dissecting some of the things that I've been interested in over the last 10 to 15, 20 years is really this idea of making my own custom tools. But that also kind of falls both in the digital realm, the computational realm, as well as sort of the physical making. Um, a lot of what I've done, both as a job at different parts. I was a cabinet maker. I've worked in construction. I've worked as a model maker for Richard Meyer's office. I've had a number of experiences, and now I have my own little wood shop more as a hobby. But something that I really enjoy is the actual physical making of things, particularly with wood and the custom joinery that you see here. Um, One of the things that's always fascinated me is this idea, the concept of Japanese woodworking. I'm sure all of you are somewhat familiar with the intricacies of their different joinery systems, but you may or may not be aware that as an apprentice during a Japanese carpenter, um, they actually will begin to develop and make their own tools. They actually have to, as one of the first steps that they do under the first several years of their apprenticeship, is to make the tools that they will use throughout their career. So they make chisels, they make their planes, they make mallets and squares and everything else that you can think of. And I found that as a kind of compelling idea. As a apprentice, as we begin developing our skill set, we also begin to develop the idea of not only of making, but also making tools that will support us as we move forward. And really, as we begin to see fabrication technology advance, we're starting to see, additive manufacturing with robotics, 3D printing, as well as subtractive fabrication processes. We're starting to see this need to make all sorts of different types of tools, and that includes the physical making of the hardware, so either hacking or modifying or building from scratch your own hardware to develop certain new workflows, as well as the digital side of that. How do we actually make our own tools to either automate our approach and make it faster or better, or develop new workflows that haven't really existed yet? And so that's really where I have focused a lot of my time and my own research. And one of the projects I wanted to start with today was a project that I started what seems like a million years ago, but probably back in 2009-ish, maybe even earlier than that, with colleague Jason Kelly Johnson out in San Francisco. And we started a project called Firefly. And really one of the key concepts for us, or for me at least, was this melding or this sort of merging between hardware and software. This, what I spoke about how we can sort of take the idea of things that can, sense the world around us, whether those are analog or digital sensors, those are game controllers, we have webcams, we have mobile devices, we have all these things around us, these objects around us that have the ability to sense or perceive the world, and we can call those inputs, if you will, and then we can define usually through code of some sort, a behavior of what we want to use those inputs to define some sort of output, some sort of reaction. So we want to control, motors or some valves or some sort of LCD screen or anything you can think of. And really that's your traditional feedback loop. For me, what became kind of apparent as I started developing Firefly is that there's this really different way of thinking about this feedback loop. Instead of being just a circular feedback loop, the traditional feedback loop, when we have this sort of hybrid model where we can take real world sensor inputs and drive a digital model, or we have parameters that like sliders or toggles, and we can use those to control valves in the real world in real time, or any combination, it really creates a new way to prototype objects or prototype designs. And for me, that came a pretty powerful or interesting idea to kind of work through. And so really what Firefly is this ability to take, in one sense, take inputs. In this case, you're seeing a light sensor, but really it could be any number of inputs and use those to, in real time, control a digital geometry. There have been other tools in the past that, processing and any number of tools, but one of the things I think that it's coupled within a 3D environment like Rhino and Grasshopper is that you have the ability to drive 3D models really quickly, prototype them really quickly. You also have the ability to send that information back out and to control physical devices like motors here, a pan tilt servo. Or we can do simulations. We can take inputs like the microphone on your phone, and as I blow into it, it's basically sending a wireless signal to the computer and simulating a wind vector to move this flag of some sort. Or using computer vision in a way where we can use our bodies to begin to control the world around us. Here, these are very simple, basic examples where we're using movement, in this case, using the Kinect, the earliest version of the Kinect, to track our body, and then based on the positioning of our body, create a behavior, whether we want to control a motor or turn on a light. One of the things I find really compelling, as I've mentioned about Firefly, is it sort of augments not only this feedback loop, but it also begins to introduce a different way of working for users, which I talked about a little bit. It takes this idea of the way most people are comfortable in working with, say, sensors and motors. In particular, there's been a real movement over the last decade using something called an Arduino, which is a programmable microcontroller. But really, a lot of times, the way you program that is through code, through writing, a text-based program, which gets compiled and then uploaded onto the board. And that's the behavior that you're using. You're basically saying, go read some information from this sensor and use it for some sort of output. But you're doing that by writing code. And a lot of times, what I've found in various workshops and teaching opportunities is that, for certain people, they don't really gravitate towards that mode of working, writing text-based software development. They have tended to work better in some instances with a visual representation, maybe a spatial representation, where I'm sure you guys are familiar with Rhino and Grasshopper, but particularly Grasshopper's visual programming environment seems to have a really nice, has opened up a lot of opportunities for people who seem to gravitate towards a more visual programming environment. And so one of the things I think is kind of interesting about Firefly is that it allows us to take something that had typically required a text-based input and move it towards this visual representation. But we also have this ability, I think, which became kind of interesting. One of the research parts is that I was looking at was how could we, reverse that flow? How could we actually take something that was a visual graph and convert it back into code that could be uploaded back onto your board, onto the Arduino board? So like I said, most of the time, the way we program these microcontrollers, for those who haven't seen it, but it's not going to pick up because of the blur. But anyway, Arduino is a simple little microcontroller but you typically have to compile it into machine language that it can understand. And typically, like I said, you need a compiler that takes some sort of text-based code. It can't really translate a Grasshopper graph for you. So one of the things I worked on was a code generator, which in this case will look upstream on your Grasshopper graph and detect any type of component that it sees and try to write the appropriate Arduino code for you. So it really does become this prototyping method where you can, use this parameters, sliders, dial everything in for your prototype, get it working the way you would want. But typically the way you would have to then do is take that and write the appropriate Arduino code to get the device to work the way you want it. Now you can skip that step. Essentially the code will be written as you're prototyping, and then you can upload it to the board and let it run autonomously without having it connected to the computer or Grasshopper or anything else. So it also, as a teaching tool, lets people look under the hood, if you will, a little bit. So, for example, if you didn't really, Grasshopper has a certain number of components, like a read map component or a constrain component. If you didn't really know what's going on under the hood, right, you just pass it in some information and it spits out some information, but you don't really know what's happening. Now you can actually go in and look at the function for these components. So another thing is that this methodology sort of begins to open up new opportunities from a pedagogical standpoint, which I find kind of compelling. But you're probably asking yourself, after looking at those simple little examples, or how do you use this? Why is this important for me? And so I wanted to show a couple projects that I've done, or at least one project that I've done, where I used this type of workflow as a way to create hopefully something new. In this case, it was really creating a new interface for robotic motion control. As I mentioned, one of the robots in particular have become pretty popular in the architectural domain over the last 10 to 15 years, primarily because they're tool agnostic, meaning you can really attach whatever you want to the end of this robot and achieve not only additive manufacturing, but subtractive. So you can do both types of fabrication. Here you see some clay printing on the left or milling on the right. It really is sort of tool agnostic in that sense, and opens up a lot of fabrication opportunities. But one of the limitations really that you see in a lot of instances is that it requires a large learning curve about not only knowing how the robot works, how to run the simulation, how to write the program itself to upload to the robot to execute its path plan. And so there's a lot of information that is typically unavailable for a standard designer. Oftentimes what happens is a designer will work on something, a project, a design, and have to hand that off to somebody with greater expertise in that domain in order to create these programs and simulations. And if at some point, if there's a collision detection or some sort of singularity that's detected, it has to send back to the designer, who has to then change the design. And it's a kind of slow and cumbersome process. And so for me, I wanted to kind of create a more intuitive workflow for a designer coming to robotic fabrication. Meaning, how could we create a tool, something that designers are already maybe used to, right? Something like a drawing tool. As designers, a lot of us are used to using tools, compasses, French curves, you name it, any number of tools to help us augment our design process. So how could we create a tool that could intuitively allow a designer the ability to control a robot during the fabrication process? And so I started with, in this case, the ABB IRB 140 robot that we had at the GSD at the time. And by extracting sort of its core joint and axis configuration, I was then able to design a controller that mimicked those same configurations. In this case, it was at a half scale. But at each case, I was able to essentially create a sensor, use a sensor, in this case, a high precision potentiometer, which essentially measures rotation. So if I use a sensor at each one of these axes, or at least pivot points, I can then determine, how much each of these joints have moved, And using a sort of forward kinematic simulation, I can sort of work up the stack and find out where the end of that end effector would be, right? So just by having 5 sensors, I can perform a really simple calculation, a matrix transformation, and find out where the center point of that tool endpoint would be. And so this was the actual device that I ended up building. And so part of this project, this was a school project, not unlike what you guys are probably encountering. This was a project that I did while I was at the GSD and took a class at MIT called How to Make Almost Anything, which was a fantastic course. And one of the things that was required was you had to fabricate and make everything in your project, including the circuit boards and writing the code and everything. So here you can see one of the circuit boards that was created on the tool tip to record or reset the tool path plan that you've created. And this was another circuit board that was created in order to essentially, this is a modified Arduino board. This is the board that takes in all the inputs, figures out the rotation information, and sends it on to Grasshopper. So as a proof of concept, this was the first step in creating a sort of a real-time simulation. You can see as you're moving each of those joints, it's performing this transformation in real time and moving the three-dimensional geometry in the computer at the same time. And because we're moving this in a three-dimensional environment, we have the ability to track where the tool endpoint is at any given time. So as I push that button, I can simply begin recording the tool path. At the same time, I was able to then translate that information into the machine language that is used to upload to a robot to execute the path that I had just drawn. I was also able to work out a real-time streaming process that could send the movement information in real time to the robot. So here you're seeing kind of the hybrid going from a physical tool to a digital simulation back out to the real world, to the real robot. And so this not only opens up new opportunities for a designer who can intuitively begin to sculpt or draw or modify things in the 3D environment, it also opens up some opportunities for, removing the user from the work area of the robot, right? Some of these robots that you look at are quite large and potentially have end effectors that could be circular saws or anything else that might have, be dangerous. And so this also offers the opportunity to remove the user from the immediate working area and also offer a little factor of safety. So that's one project that sort of begins to meld some of the concepts that I was using in Firefly, or talking about with Firefly, sort of this idea of making in the physical world and also making in the digital world, and combining those using sensors or actuators or any combination. So for me, that's really where I find a lot of the work that I find interesting, is this ability to kind of combine both of those worlds, because I do really enjoy getting my hands dirty, making things, as I'm sure or hope that you guys do as well. But at the same time, we need to start to think about how we can use new tools like a robot and begin to augment them to create new opportunities. I think I'm going to switch gears a little bit and now talk about a second project, which is still in the same vein, but this was more about my research as my doctoral research at Harvard. And one of the things that became important for me was a simple question: what does it mean for architecture to be smart? I'm sure if I were to ask each one of you to give a response to that question, you'd probably have a pretty accurate but also a diverse set of answers to that question. And really, that's because there is no definition that meets all of the criteria. For each individual person, smart architecture, smart cities, smart environments, we hear a lot of that. there's really no definition that has some sort of true consensus. We've seen the evolution of intelligent buildings, starting in the 1980s, where we had systems that were sort of separated and not really communicating to one another, all the way up to newer technology stacks today, which are fully automated, fully connected systems. And that's really the evolution of what we call these intelligent buildings. But if we think about the control strategies, up until relatively recently, they've all been reliant on this idea of what I call a reactive or automated model of control. You can think of it sort of like a thermostat, right? The sensor detects a rise in temperature, and so it's then programmed to kick on the air conditioning. It's a relatively simple reactive system. There's no way for the system to begin to understand how the space is being used, or use any kind of capacity for learning or reasoning. And so that was something I became kind of interested in as part of my topic for research at the GSD. In particular, one of the things I really wanted to focus on was thermal comfort. It's been shown, again, this is sort of a condensed version of the research, but there's been a number of studies that have shown that thermal comfort in particular is one of the key factors that come into play for occupant satisfaction or dissatisfaction, if you will. There's some pretty big numbers out there of like how, in particular, temperature and privacy settings essentially really affect occupant satisfaction, particularly in an office setting. And that's something I should have mentioned, that this research was really looking at how can we augment the environment around us in an office setting. And really the key here was looking at thermal comfort. And there was a number of studies developed in the 70s and 80s by a guy named P.O. Fenger, who really boiled down, and this is how the ASHRAE standard is set up of how buildings are controlled today, is something on this what's called the predicted mean vote. And it boils down into these 6 different factors, essentially. There's air temperature, there's mean radiant temperature, there's air speed, and there's relative humidity. Those are the 4 environmental factors that come into play when trying to predict whether an occupant will be hot or cold. The 2 personal factors are how much clothing is a person wearing and what is the amount of work that they're doing, right? Are they digging a ditch or are they sitting in a chair? So what is the metabolic rate or the amount of work that they're actually doing? Those 6 factors go into a large equation and essentially will give you a value somewhere between -3 and +3, which predict, if the user is going to be slightly cool or too hot, the ideal being somewhere around 0. And then using another graph, we can predict the percentage of people who would be dissatisfied using that predicted mean vote. What I find a couple things interesting too. One is that you notice the graph never hits 0, the graph down here. So there's always going to be, at least according to this graph, 5% of people who are always going to be dissatisfied with their space, which I find kind of interesting. And secondly, the ASHRAE standard is set up to allow for basically the standard says, it's okay as long as we fall within 80% satisfaction rate, which to me is, we can do better. As architects, as engineers, we should be striving to do better than 20% of people in our spaces being dissatisfied every day they come to work, right? If you think about the labor force, you're talking about millions of people who show up to work every day who are generally going to be dissatisfied with the environment around them. And to me, that's a problem. So I developed a tool. A lot of the research that I focused on was developing a neural network tool that was built on this idea of the predicted mean vote. As I mentioned before, there is an algorithm that you can plug in, that you plug in those 6 different factors, and it will determine what the predicted mean vote will be, right? So here, the left-hand side of this interface is really about using that algorithm that this guy P.O. Fenger developed. So you can see you're moving these sliders, and you can see the predicted mean vote and the percentage of people being dissatisfied. Here, you can generate basically random data. You're randomly assigning all of those 6 different values and creating 5,000 different iterations to determine, this is generating some training data in order to feed into what the next stage would be, the neural network training. So here, what we're doing is taking those 5,000 sample points, and we are going to try to create a neural network which can get as close as possible to that predicted mean vote output. So the way a neural network, and again, as I mentioned, this is sort of a condensed version, but the way it works is you have some inputs, and it tries to predict an output. In this case, the input is those 6 values, and the output is going to be the predicted mean vote, right? This number between -3 and +3. So you're feeding in those values, and as it learns, essentially it's adjusting the weights of all those neural networks so that at first the output that it gets is going to be really far off. But ideally, some of these are off. Ideally, what's happening is that as it learns, that predicted mean vote will get closer and closer to the true value. So here you can see I'm basically coming up with some different settings, and I can start the training, and there you can see is the error rate. Essentially how at first what it was predicted and what it should have gotten was pretty far off. But eventually, as it begins to learn, that prediction becomes much closer to reality. So the next step is then to give it new values, right? Now I can load in the neural network and give it different values and see, what the predicted mean vote would be. But now it's using the neural network output instead of this the algorithm. And so here I can take those same 5,000 samples and run. The red in this case would be the initial values, and the blue are the outputs from the training set, from the neural network. And really what you should see is a graph that overlays on top of each other fairly closely. You're probably asking, why are you doing all this work? You already could predict it using the algorithm, so why are you doing all this work? Well, the key here is that neural networks have the ability to adapt over time. So if in this case, the value thought it was at 0, but I change it to say, well, in this sense, the user actually was quite cool. They thought the setting was cool based on these, different factors. I can retrain the network based on this new value. And now when I run the setting, you'll see that there's a shift in the neural network. So what it's done is it's learned how to augment the settings based on the feedback that was given from the user. So if we look at this, we have the true value starting off, which is based on the average user, if you will, based on all these different settings. But as we begin to give it feedback from the user, the neural network can begin to learn and adapt the space accordingly by either shifting to the warm side or shifting to the cool side based on the feedback that it's getting. And so it has the ability to adapt to each individual user and how it's being used. So that was one aspect of it, which was the software side. The other side was sort of looking at the hardware. And this was sort of a diagram that was put together to show how things communicated with each other. But I wanted to show a few things that were developed from the hardware side. One of the things I had to do was be able to determine the environmental settings inside a space. So this was a wireless sensor that I developed that detects temperature and humidity, motion detection, as well as light levels. And this was sort of the enclosure that got built into. There was another thing that I wanted to develop, which was an AC power adapter. Now we are used to seeing Alexa, that you can buy these things for Amazon, which will wirelessly turn on and off anything you turn on to it. My 5-year-old has a Alexa smart plug that was probably $20 that you plug in and say turn on the smart plug, and it'll turn on his lamp next to his bed. But 5 to 7 years ago, when this research was being done, that didn't exist. And so this was a wireless power adapter that could wirelessly turn on whatever you plugged into it. And that would help because I could plug in a heater or a lamp and then be able to communicate with that particular device. Because what you see in a lot of office spaces, right, and I have some of this research in the dissertation, but there's been some really interesting case studies of like a LEED platinum building, which has been engineered to be, fully sustainable and have, the best environmental settings you can. And if you walk through, what you find are personal heaters below the desk, or a desk fan, a task light, earphones over the desk. And all of that is because people are not the average user. Everybody has different preferences, and they need to augment their space. And the only way they can do that are to bring in these personal devices. But what then happens is there's no way for a heater to communicate back with the central building system, right? So a user might be cold, so they turn on the heater under their desk, and then the thermostat detects a rise in temperature, so it kicks on the AC, right? So now you get this negative feedback loop, which is causing, a waste in energy expenditure, but also making the occupant even more dissatisfied. So with this type of device, now I can create a system where a personal heater can then also communicate, and sorry, there's a typo here. This was an IR emitter. In the study that I ended up using, I was using a HVAC unit, which could be controlled with a remote control. So I essentially was able to create an IR emitter, which could send signals to the HVAC unit to tell it to turn on, the air conditioning, or turn off the air conditioning, or set it to this set point. So by creating these devices, I was essentially able to create an environment that would allow your personal heater the ability to then also be able to communicate back with your HVAC system, right, through this wireless remote control. Probably the most involved of the hardware was this idea of a personal desk fan. And one of the things that got me excited about this is that some other studies have been shown that you can save anywhere between 17 and 48% on your cooling energy savings by using a low-powered fan to offset the impact of increasing the ambient temperature in the room a couple degrees, right? So instead of keeping everything at 72, if we turn the thermostat up to 76, but then use a really low-power fan on each person's desk, we can save a substantial amount of energy. And if we, work out the math here using an average kilowatt per square foot, it works out to potentially $1.5 billion that we could be saving by using, just simple devices like a fan in a room. So it has a potential for a fairly large financial impact. But one of the things I wanted to do was try to take the idea of a regular desk fan and make it ideally a little bit smarter than a typical desk fan, because not all desk fans are low powered, for one. So this particular desk fan has two 3-watt fans on the sides, but it also has a webcam built into the bottom, and it has the ability to use facial recognition to track where the user is and only direct the cooled air toward parts of the body that most affect comfort. There's studies that show for cooling, you want to focus the air mostly on your face and neck regions. For heating, it's more the feet. So really what they found is people tend to show the best results in a sort of asymmetric thermal environment. It's not like everything around you has to be the exact same temperature. In fact, our bodies tend to like certain things cooler than other parts. And so I designed a fan that could then be low power, but also try to really focus the cooling where it's most needed. So here you can see sort of an exploded axon of all the different parts in the fan itself. Here are all those parts sort of laid out before final assembly, and then this is the final unit. And they're actually, I built 4 of them. I can turn off the blur on the fan, but they're sitting on the shelf behind me. I'm going to try to play a video. I don't know if audio, I may need to actually, yeah. I'm going to try to play a video, and hopefully the audio will work on your side. Marshall, will you let me know if the audio is not working? It's not going to be the end of the world if it doesn't, but hopefully the audio will work for you guys.
Yeah, I'll let you know.
Meet the new smart fan. This little guy is designed to be the
I can hear it. It's a little low, but I can hear it.
Hang on, let me turn it up the volume. It looks like it's already up.
Meet the new smart fan. This little guy is designed to be the smartest smart fan ever invented. He has the ability to learn when and where to focus his attention, using facial recognition to direct cool air towards parts of the body that most affect comfort, like your face and neck. He's also smart when it comes to energy. Studies show that we can save a substantial amount of energy if we raise the ambient temperature in a room just a few degrees and use a low-power fan to cool off the body. Yet most fans only have the ability to perform 1 of 2 actions. They can either sit still or oscillate back and forth. Because most people don't sit still or rock back and forth all day, regular fans waste an inordinate amount of time and energy cooling the area around the actual person. Needless to say, that just blows. The smart fan uses 2 small 3-watt fans, drawing about 1/3 of the power of a typical desk fan. Plus, with his built-in video camera and facial recognition software, he spends all of his time and energy making sure you feel good. The smart fan also has the ability to communicate with everyday devices like task lights, personal heaters, and larger building control systems. And as if that weren't enough, he also uses state-of-the-art machine learning algorithms to get better and better at maximizing your comfort. Smart, right? Welcome to the future of personalized comfort control. Your personal desk fan just got a whole lot smarter.
So that was a video that I put together also as part of this research. All of this to say is that this was all 3D printed parts, stuff that you can get off the shelf. This is nothing that I really did that is in building these things that is out of the scope or possibility of stuff that you guys could build. Obviously, it took some time to build all of those different parts and develop it, but I feel like part of what I'm hoping to show or inspire today is this idea that you can really make any and all of these things. It doesn't have to be mass produced. Those were 3D printed enclosures that were sanded and painted. Really, it's really hopefully giving some confidence to be able to say, a lot of this stuff is achievable, even just on your own, even using just your own fabrication tools. I wanted to cover just a couple of different quick things that basically, through the study that was done, we were able to show that there was an energy, most of the time, except for one anomaly, there was an energy decrease by using the system. There was 3 different phases, one with just using these devices without the neural network, and then a second phase with the neural network. We were able to ask the users questions about whether or not they were satisfied, and typically the satisfaction level increased over time. Their desire for more control decreased. And that was correlated. So the desire for more control was correlated with the actual user interactions with these devices. So you would expect if somebody had the desire for more control went down, it would also indicate that they were turning on and off the devices less. And so here you can see the devices were turned on and off less because they didn't really need to. It was sort of adapting for them. As well as, and this is a notoriously hard thing to measure, but productivity or the perceived productivity gains from the environment increased as you began to use the system. So there were a number of interesting results that came about through this type of research. All right, I've got one other project, which is kind of a departure from what I've shown thus far, but it sort of talks about a project that I did with another colleague, a professor at the GSD at the time, Panagiotis Michelatos, who Marshall knows well. And we started on a project at the same time that I was doing this research about 3D printing. And essentially, I had this opportunity of working with Objet, who then was bought by Stratasys. But if you are unfamiliar with their 3D printers, they're pretty amazing because they have this ability to do multi-material 3D printing. I believe they now have models that can do up to 4 different types of resin. But essentially, we have the ability to control the deposition of different types of materials. So not only color, but also opacity as well as structural. They have soft rubbers and they have harder materials. So we have this ability to do some experiments with this multi-material 3D printer. And one of the things we started to realize is that the hardware had really progressed more than the software side. And what I mean by that is we now had a hardware that had the ability to deposit material in any different spot within a 3-dimensional volume. But the way we designed objects was still largely using this idea of what's called a boundary representation. You guys may be familiar with something called a BREP, right? That's short for boundary representation, where you define the boundary volume of this object, but then everything inside is treated sort of as a homogeneous type of material, right? If we were to take a section cut through this, this would be sort of a solid homogeneous material. And so really the way we think about 99% of the tools that are out there are using this idea, of a boundary representation. And we started to think there's got to be a better way, especially for controlling volumetric material deposition. We looked a little bit towards this idea of the assembly paradigm, about how instead of taking instead of this one homogeneous part, how do we start to take this idea of individual parts and linking them together, as well as looking at other models that are out there that are not used typically for design. In this case, one of the ones, so there's been an alternate representation model out there called voxel representation, which I'll talk more about in a minute, but it's heavily used in the biomedical fields, particularly for 3D reconstruction of MRI scans and CT scans. So here you can see some brain scans which take 2-dimensional slices through the brain, and we can create a 3-dimensional model by reconstructing them in this 3-dimensional form. And so there's representations out there that begin to speak towards this idea of how do we begin to understand how material is placed within a 3D volume. It's just not, or hasn't been up until recently, available in a design package. And so here you can see a slice through. This is very different than that bunny model because now we can see the density of the tissue layers is quite different throughout the volume. So what is a voxel? A voxel is really just a 3-dimensional pixel, or it's a structure that is able to store information within a 3D volume. If we think about a pixel, right, we have an image that's a 2-dimensional image, and a pixel is just a atomic element, in this case a square, but an atomic element that can store information about that particular space in the image, right? So we have different things called channels like red, green, and blue, and they control the color of that spot on the image. Well, a 3D voxel is very similar. It's just that instead of 2 dimensions, it's working in 3 dimensions. So instead of being a square, we can think of it sort of like a cube, but really it's just a data structure that stores information about that particular spot within a volume. So what we decided to do was think about how can we create some different types of channels or ways to store information within the volume in order to create a way to distribute material for this three-dimensional multi-material, or this multi-material 3D printer. And so what we came up with is this idea of two different channels, one that controls the shape of the object and another that controls, say, the material ratio. In this case, what you're seeing is the top one sort of defines the global shape that you're going to print, and the bottom one is controlling, in this case, just a linear gradient between two materials. So it goes from black to white, where black will be one material. In this case, when it gets 3D printed, it will be the blue, and the white will be another material. In this case, it will be the red material. And any combination between the two, we can really create infinite gradients between those. And so the way the shape channel works is there's something called a level set or a threshold, where essentially, if you think in a two-dimensional image, we think of a value, a grayscale value between 0 and 255. That's usually the standard value for brightness. And so what we can do is define a threshold, let's say 128, and any pixel that is below that threshold will be considered inside, and anything that's above that threshold will be outside, right? So it's just defining a boundary based on some sort of threshold. And we can think about that same idea in a three-dimensional volume, where you essentially create a three-dimensional volume or image, if you will, in the shape, and then we just determine, using a marching cubes algorithm, it essentially creates a surface depending on what's going to be inside or outside based on that threshold. So here, going back, we can composite those two different channels together to create one final output. So I'm going to show a couple of different working techniques that we developed. This is a tool that we developed called Monolith, which was eventually acquired by Autodesk. But this is a design platform that we developed to essentially allow a user to control voxel-based modeling. And as I said, really up until this point, I would say 99.9% of design software out there had been mostly built on this boundary representation model. And so this was a new way of thinking about design. And so these are some of the different techniques that we created. One, in this case, is this idea of painting. So you can paint a shape in the three-dimensional volume, and depending on the layer that you're on, whether or not you're on the shape layer or the material ratio channel, you're defining those different attributes. So here I'm drawing in a 3D shape. That is defining the shape channel. So you can see it's creating those volumes. Now I'm in the material ratio channel, and I'm sort of painting where I want different materials to be. Another thing that kind of is interesting, you'll see in just a second as I change the slider. Sorry, these are kind of fast. Is that we can apply, because we're taking stacks of, it's not really stacks of images, but the idea is kind of similar. We're extending the idea of a pixel to a three-dimensional voxel, right? So we can take lots of similar image editing techniques like blurring, right? All of you are probably familiar with using Photoshop or some image editing software which blurs the image. We can take those same ideas and apply it to a three-dimensional model. So here we're using a Gaussian blur filter to sort of smooth over the model and blur those voxel values. So here you can see we're just changing the Gaussian blur and to make it more smooth. Another thing we can do is we can define, we can apply mathematical formulas. So take the voxel value, each voxel values x, and multiply it by the y value and the z value. So take those coordinate values and multiply them together and get a three-dimensional shape, right? So we can take any number of mathematical equation or use a preset, so like the gyroid or Schwartz surface or any number of mathematical equation, and apply those to either the shape channel or the material ratio channel. So here we're creating mathematical surfaces, or we can take images. In this case, you're seeing I'm taking two images together, in this case sort of a radial blur and then this cross, and I'm doing a loft or a sweep. If you're familiar with Rhino commands that do a sweep, or a loft together, we're taking those two images and sort of blending from one shape to the other shape. One of the things that voxel modeling is really good at is this blending between different shapes. So here you're seeing this fillet between, as it comes down between this cross and intersects with this tube, we get this really nice fillet. And that would be really difficult to do using a boundary representation model. Now it's easy. I mean, using a voxel-based model that's one of the benefits of using that type of technique, is that we get very smooth transitions between objects. Here we're doing the same idea, but instead of just doing it from top to bottom, we're doing it in 3 different directions. So depending on the image we use, we can begin to create different types of sweeps or lofts throughout the volumetric field to create different types of geometry. Again, another thing we can think about is this idea of taking that boundary representation that I mentioned before, but now being able to really control the material deposition in the volume, inside the volume. Another thing that's pretty interesting, I think at least, is that, and again, I wish we were in the same room so I could get a show of hands, and most of you have your cameras off, but I'm sure most of you have probably, in the course of doing some sort of modeling exercise, you've had to perform a Boolean operation, right? Whether you're either adding 2 objects together or removing one object or taking the intersection. We can do that with images, and a lot of times with boundary representations, if you get complex forms, those Boolean operations might fail, right? Because it's really having a hard time figuring out how to remove one object from another. Well, with image editing, all we're doing is stacking those together and either removing, subtracting, or adding the pixel value above it onto the one below it. And so it's very easy to create objects that begin to blend or do Boolean operations. In this case, we're doing sign distance fields, but what you'll see here in a minute as I add another shape layer is I can create a line that is intersecting with a point. And here you can see they smoothly blend or Boolean together because I'm adding them together. We also have the ability to create cage-like objects where we can sort of sculpt within a cage, and we can change the different interpolation factors. But essentially, we can change the values of different points in a space and begin to create objects that, again, would be quite difficult to do by hand modeling. But now that we're doing it within this voxel field, we can create very smooth transitions and relatively complex forms. The other interesting thing I think that we began to explore is this idea of this mesoscopic or microscopic deposition of patterns. So not only could we create forms at the global scale, which I just showed, but we also have the ability to take smaller patterns and propagate them through a volume. So for example, we can, here we have a linear gradient going from white to red in this case. But we can give it a pattern, in this case sort of like a 3D cross, and it will smoothly tile in between that to achieve that gradient that you were just trying to create. So if we want it to go less red and more white in this case, or you can see that the tile object here is this 3D cross, but as it needs to become more opaque, it seamlessly transitions into this object that's more dense, if you will. So we have the ability to create really interesting patterns throughout the geometry by taking sort of a 3D cell, if you will, and propagating that sort of the way you would a UV map, but now we're applying it in UV and W. And by controlling the UV and W patterns, we can create not only optical different patterns, but also structural, right? So if you can imagine white and red here are different types of maybe hardness or density, where you have more rubbery materials, you could really achieve lots of different types of effects. So here are just a number of different examples. We also have the ability, and this is another example of how we can create those different cellular patterns. So one idea is to create, so just like I showed, we can create images and create a 3-dimensional volume. So we took the radial blur and the cross, and we created a sort of sweep between them, or the other one, which was creating it sort of in the X, Y, and Z. We can take that same idea and use that as a cell that we use to propagate through so we're taking that global form and using it at sort of the micro scale or the mesoscopic scale. So here, what we're doing is I'm just creating a texture in Photoshop, and then we're going to use that texture as a way to create this three-dimensional volume. So here I'm creating just a shape. In this case, it's the gyroid shape, and creating a linear gradient through here. And then what I'm going to do is apply that texture that I just created. So there's the cross, and I'm going to create a texture, and I can determine if I want to extrude that in the Z or the XY or multiply it. And it really gives me the ability to create these sort of mesoscopic patterns throughout the volume. So I can create like a cage-like structure, in this case getting denser at the bottom and more transparent towards the top. Now the other thing I can do is I can actually say use current model. So in this case we had a gyroscope, right? A gyroid as our three-dimensional shape. I can take that gyroid and say that as a pattern and then apply that, as a sort of mesoscopic scale pattern throughout the shape. So you're taking the global form and using it as a patterning technique throughout the object. And so here it's using the gyroid as the pattern that it will propagate through. The nice thing about a gyroid is that it's triply periodic. So it has the ability to connect on all three sides. And here you're looking at our slicer. So you can imagine cutting this thing in slices to see, the differences between what is, one material and what is the other. So here, one of the things that we found really compelling about using multi-material 3D printing and using this voxel representation is because we're in this three-dimensional voxel field, we have the ability to make slices which create those 2D images. And what's interesting about object printers as opposed to, say, something like a standard 3D printer, a standard 3D printer is using G-code most of the time to, move the motors in different ways to show where, the head needs to go. In this case, it's using an image, and where it's actually using two images, where a black pixel means don't deposit any material, white is deposit material for this particular head, right? So in this case, red would the red nozzle would get this image, and the white, or this would get this image. So it's basically, we can take a slice through the voxel field, extract the slice, and then determine the two bitmaps to be sent to the 3D printer, which can then control the head of the 3D print. And so we can really get down to the very microscopic. Each individual drop of resin in the print head can be controlled through this, technique. And that's called bitmap printing. And so here you can see you can create patterns that have the ability to create anisotropic material deposition. So if you wanted it to bend in one way but not in another, so here you can see it's almost like creating an artificial wood grain, right? You have wood grain that's going this way, so it's stiff when I try to push it together. But in this case, if we run the grain this way, it's stiff in the opposite direction, or it doesn't give us the same stiffness as this pattern. Here, we also have the ability to create optical occlusion, so based on different viewing angles. So here, because we're altering it throughout the volume, if you looked at it head on, it would look like a gradient. If you tilt it, it's almost like a micro louver system and begins to occlude objects behind it. Another thing that would be completely impossible to do without bitmap printing is this idea of hairline features. So imagine creating curves throughout a volume, and you have to create meshes for each of those objects as STLs and then try to 3D print those. It would be incredibly difficult with the resolution to get to that fine scale. But because we're doing bitmap printing and because we can control the deposition of the model, here you're seeing stress lines as if he's pushing down on the object. This would be the stress lines that would be induced into this object, but you can actually see through it because we're doing multi-material printing with clear and opaque resins. Here you can actually print the hairline distribution of those stresses. Another thing that voxel modeling opens up is this ability to do certain simulations that would be difficult in any other way, which in this case is called topology optimization. Topology optimization is, for those who aren't familiar, is a way to create a load case. In this case, you saw where I'm defining a load on the top and two supports in this case. So you're defining how a load is going to work its way through a volume, and then you let the solver determine what's the optimal shape depending on those, that load condition. So here you can see if we had to support a load on the top and only have it touch down on two parts on the floor, this would be the optimal shape that would be form found in this object. So we have the ability to create, structurally optimized objects, and then of course we can also begin to extract principal stress curvature throughout the volume, and we can also export those curves as well. So we could begin to either 3D print those or export those as curves into that volume. Topology optimization has the ability to create really intricate or complex form finding processes. So in this case, it was started with a chair, right, or the volume of a chair, and form find what is the optimal shape of this chair. Or we can create and sort of confirm certain ideas, right? In this case, we have a distributed load on the top and two support conditions. And if we think about how we might go about solving that from a statics perspective, for those of you who are taking structures, you'd say that's going to be a truss, right? You probably will define a truss that to support a distributed load that comes down on 2 points. In this case, topology optimization confirms that, right? So here you can see this is the optimal shape based on that condition, and we can 3D print using sort of a clear, softer material and a opaque, harder material, and get these sort of bone-like structures, these structures that are denser where the material is needed and softer where they're not. An alternative to that would be printing. This is actually printed in metal, stainless steel, where we're applying those patterns, in this case a gyroid, at the density level that is found here. So here it gets denser where the material is needed most and becomes more translucent where it's not. It also has the ability to generate forms that would be otherwise really difficult to even conceive of. Right? We can not only can we 3D print these really complex forms that would be difficult to fabricate in any other way using different densities, but in this case we're actually having to solve the same idea of a leaf, right? We have a support on one end and a cantilevered load on the other. That's the same structural load case as a leaf, right? We're connected on one end and it has to support its own weight. And so what ends up form finding in this volume is a sort of three-dimensional venation or veining system that would be very difficult for a designer to come up with, but in this case actually gives us very unique and intricate problems. That's a very long-winded way of, I don't really have a good wrap-up slide here, but I hope a lot of the stuff that I showed today at least sparked some discussion or maybe some interest from a couple of you. And I'm hoping maybe you guys have some questions for me based on anything that I showed. I don't know how I did on time. I might have been long-winded.
It's pretty good. Yeah, let's see if anybody has any questions. I have some if no one else does. Thanks Andy for presenting your work. It's always amazing to see the things that you're working on and the breadth of your research in many different areas. Does anybody have any questions for Andy?
Don't all start at once.
Well, I have a question. So obviously I've known you for a while and I've seen this research develop in many different different ways, and like the tools that you have created have been useful. You were one of the earlier sort of adopters of Grasshopper. You even wrote like one of the first primers on how to use it well, I think before I even started using it. And so you've been good throughout your career at either adopting or creating strategies that will in the future sort of become important. And you can see that in your development of some of these systems that seem almost commonplace now, but you developed it at a time where they weren't even sort of thought of, like the Nest as a learning thermostat, maybe using some of the same sort of algorithms that you use to develop your learning thermostat, some of the smart plugs that you mentioned, all done well before any of that stuff was sort of a consumer product. Some of these other systems for modeling or developing smart buildings, looking at robotics, sort of looking at many different things, all sort of future focused to what could potentially be useful in the field or other fields. And you've been super good at sort of speculating about what things could happen. So that being said, could you speculate on what might happen in the future? And I know that's putting you on the spot, but like, where do you see things changing? What are the things that are worth working on? What are the future advancements for you that we might see in 5 to 10 years?
Yeah, sure. Thanks. That's a great comment. And first, I'd like to say too that a lot of this is also collaborative work, and so a lot of the work that is shown is not just for me. It's also about bouncing ideas off of other people and getting their feedback and their input, and also their work. And so I have been lucky and fortunate to be able to be in certain spots at certain times to be able to capitalize on some of those things. But I'd be remiss if I wasn't, at least thankful for the opportunity to work with so many really smart and brilliant people that have also influenced a lot of the work that you saw. To start answering the question itself, it's a fun and also notoriously difficult question to ask. I mean, if you or question to answer. There are lots of
fun question to ask, a difficult question to answer.
Yeah, there are people out there whose whole role is trying to predict what the next 20, 30, 40 years are going to look like. Mostly they're writers, but I think for me, the low-hanging fruit, I would say, in the next 5 to 10 years span is not all, but a lot of the low-hanging fruit is going to be looking at machine learning and sort of machine learning, artificial intelligence, choose your term, but using algorithms that can begin to adapt or learn or make predictions based on different scenarios. I think you'll start to see that. I mean, you're seeing it everywhere in non-design settings. You see it in our phones, speech recognition, mapping, Google Maps. All of the Facebook is using machine learning to make predictions about what it thinks you want to look at. All of that stuff is heavily around us, and to the point where it's so ubiquitous that we don't really even notice it anymore. We've kind of, it's just become part of our day-to-day life. And I think architecture is notoriously slow at adopting things and being able to, there's so much inertia with architecture practice in general that it has a slow ability to kind of to move, to catch up to different things versus, tech startup companies that are trying to, really push the boundary. They're able to move much quicker on certain problems. But I think what you'll start to see is architecture in general and design move into that realm of how can we implement machine learning algorithms to make design better or make design more automated or give us things we weren't really thinking about. Now that opens up a lot of interesting and ethical questions about, where does the architect or the designer fit in this idea of like if algorithms are starting to develop forms or shapes or designs that we weren't necessarily the primary designer, right? We set up the conditions and let it give us some designs back. How does the architect, where does the role of the architect play? And that's been a question since the 60s, right? A lot of writers have been looking at that since the 60s or even earlier about what is the role of the architect if, the agency of design gets put into a different bucket, right? The design process is taken over by a sort of automated process. Does the designer just become someone who picks the right design, a picker of sorts, or are they the person who's really orchestrating all of the parameters at a higher level, which feed into the form finding process? And so I think it's going to be an interesting question for those people who are interested in developing their own tools or into the developing world and using machine learning in that realm. But I think you're also going to start seeing, architects and designers have to change their role a little bit. They're not, and that's probably going to be a difficult transition, right? A lot of designers don't want to give up that agency, and so I think one of the things you're going to see is this pushback of adoption of whether or not a designer wants to embrace this new technique, which may give them designs they hadn't thought about, but then take some of the design freedom away from them, versus will they completely reject it? And I think that's going to be an interesting question as we move forward. But I would say the easy answer to that question is going to be the machine learning side. Outside of that, obviously, I think you're going to start seeing new ways of fabrication is constantly sort of evolving, thanks in large part to academia and certain industry partners. But a lot of the stuff, Marshall, I'm sure you're aware with all of your carbon fiber weaving and stuff like that, and there's other people looking at origami folding and casting that. And so I think there's a lot to be explored still in the material science space and how we can use fabrication differently to achieve new types of design. So I would say really, and that sort of goes back to how I was expressing the talk here, which is this merger between, there's still a software side and a physical side, but I think when we start to bridge those two is where we start to see some of those opportunities. And so maybe it's machine learning, which is leading towards fabrication, or some sort of combination of the two, which is really the where you want to position yourself. But I'd say those are the two spaces that I could see moving forward that are going to be pretty interesting to watch.
Yeah, and you're already starting to see a couple of things like that, pop up, even at Autodesk, right, with their sort of like generative design software for space planning and things like that. I'm sure there are other potential applications that get into machine learning for fabrication or machine learning for other sort of design strategies that could be ways to think about it. I like that you bring up the idea of agency and what that does for agency, and I'm wondering if you think if it's a reduction of agency or a shifting of agency, because at the same time you might say that you're getting rid of some of the agency by relinquishing some of that to these machine learning algorithms, or if we've had that conversation about parametric design or anything like that in the past. But you're also democratizing other technology that gives us more agency, right? With our fabrication, sort of saying, instead of passing it off to somebody that's fabricating, you're sort of making your own tools so that you have more agency in that realm. So is it do you think the architect's role is reducing as a designer, or shifting as a designer to where they have more agency in different areas as technology is changing?
Sure, that's a good question. I personally think it's more of a shift. And we'll see if it even happens, right? All of these could be predictions that never come to fruition, but
Mhm.
I certainly think it's more of a shift. Architects have, in my opinion, architects have been really good in their role throughout a project scope has been about the orchestration of the different parts, right? They're constantly meeting with engineers and consultants, and they're the one who has to be the client liaison and know everything that's happening with all of the different systems. They may not have the expertise in structural engineering or civil or any type of lighting consultant, but they know enough to be able to orchestrate. And that's one of the hard parts about being an architect, is being able to know enough about all of these different domains to be conversant and be able to actually manage a project at this holistic scale. So I think really it's just a little bit of a shift. Instead of saying, you're now only focused on design, really the role of the architect for me has always been about this orchestration at a higher level. Yes, they do work on the design also, but it's also about coordinating all of these different aspects. And so for me, I think the machine learning still has, at least at this point, is still going to require a lot of manual input from the user as a design input. So for instance, like the load case, setting up those load cases and stuff like that. Yes, the end result is going to be this form found object, but the designer had to create the initial conditions to be able to run that. And you'll see that with multi-criteria optimizations or any number of other algorithms that you end up using. Someone still has to do that initial input. And so I think really what you're going to start to see is a shift from the designer's perspective from drawing every curve and every line to the sort of orchestration of the various parameters. And I think you've also already seen a bit of a shift in regard to the other idea, which is, if you think about optioneering, which I kind of dislike as a term, and I don't think designers, at least right now, enjoy the idea of optioneering. But at the same time, if you think about how most buildings are constructed, they look at off-the-shelf parts, right? You're looking at glazing systems or elevator systems that are or structural systems that are sort of off-the-shelf known commodities. A lot of details, stair details and stuff like that are sort of picked from a catalog of things that are already sort of available and say, okay, we want this design to look like this. Yes, there are a small percentage of projects that can be completely customized, but in a large part, given budgets and manufacturing techniques, a lot of things are, just selections, right, of different finishes, selections of different products, selection. And so a designer is going through and already working with this finite set of pieces and selecting them for a project to make them the most effective. And so I see that already as a precursor leading into this idea of like design can be that next step, right? You're basically already cognitively in that space of thinking, okay, I'm just going to be selecting from the best criteria of what's available. I think you're already seeing some of that shift into that space, right? And so for me, I don't think it's going to be too far off where the architect's role has already begun to augment in that direction.
Yeah. Well, thanks, Andy. Well, let me ask if anybody else has a final wrap-up question. I'm assuming since you don't talk in most of the classes that you don't, but I want to thank you again, Andy. As much as I enjoyed your sort of like future thinking development of all these projects, in the same respect, I would almost like to see the ideas that didn't work out. If you have the lecture on like the flying cars and the jetpacks, it would also be great to see. But thanks for joining us and thanks for the conversation. I really enjoyed it. It was nice to see you again as well.
Yeah.
Hopefully I can have you back some other time in the future.
Yeah, that would be great. And I just want to thank all you guys for sitting in and listening to me talk. And feel free to follow up. I should have put my contact information, but Marshall can give it to you. If you want to follow up with any questions, just let me know.
Great. Thanks. For everyone else, I've got a couple more minutes before the end of class, so I'll head up to studio. If you guys have any more questions about your projects, I can talk to you about that. Thanks again, Andy.
Yep. Thanks, guys. All right. Bye.